In part 3 of the video series for Chapter 3 Explaining Motion, I will discuss the difference between mass and weight, and then I will talk about Newton's third law, also known as the law of action and reaction. Mass is a property that all physical objects possess, and it is related to the amount of material that is contained by the volume of an object. Mass is defined as the amount of material or substance or stuff contained in the volume of an object. So for a solid object, the volume doesn't change. Therefore, the mass of this object will remain constant at all times. Mass is a scalar quantity. Mass is a scalar quantity and only depends on the volume of the object. Mass only depends on the volume of the object, provided that the material from which the object is made remains the same. So for the same material. Since mass is a unchangeable quantity, that means that if we take an object that has mass 1 kilogram here on Earth to the moon, this object will have still a mass of 1 kilogram. The mass doesn't change. However, the next quantity that I would like to discuss, which is related to mass in a certain way, the weight, can change. Let's see why. Unlike mass, weight, or the force of weight, is a vector quantity. It's a force. As opposed to mass, which is a scalar quantity and it doesn't change. So, since weight is a vector quantity, it can change. And how it changes is described by the definition of weight. Weight can be simply defined as the gravitational force that acts on the mass of an object. So, for example, an object with a fixed mass is placed somewhere close to the surface of the Earth. If we let go, this object will fall towards the ground, and that is because gravitational force acts on the mass of the object, and as a result, the weight of the object is the force that makes it move down towards ground. So how is weight defined? The formula for weight, which we are going to label with W, says that the weight W is equal to the mass of the object m times the gravitational acceleration g. So g has a value of 9.8 meters per second squared. So this is gravitational acceleration. And this value can change depending on where this value is measured. Meaning, on the Earth, the value is 9.8 meters per second squared. On the Moon, this value is about 6 times less, something like 1.7 meters per second squared. On Jupiter, it's much bigger. On the Sun, even bigger than that. So the value of the gravitational acceleration changes depending on what celestial body produces the gravitational force. That means that since the weight of an object is calculated as the product of mass and gravitational acceleration, if you take a 1 kilogram object from Earth to the Moon, the weight of the object will be different because the gravitational acceleration value is different. So mass, being a scalar quantity and defined as the amount of substance or material in the volume of an object, doesn't change no matter where you measure it, but the weight of that mass can change depending on the value of the gravitational acceleration, because it can change depending where you measure it. So let's summarize. The weight is a vector quantity. The weight can change depending on the value of the gravitational acceleration. Here I want to make an important note. For homework, for gravitational acceleration, use 10 meters per second squared. This is the value that was adopted by the publisher, so for homework, use that value. Now let's do a quick example using the definition for weight, and then we will talk about Newton's third law. What is the weight of a 20 kilogram block of steel? So what we know is the mass of the block, 20 kilograms. And since I'm looking for weight, I also know the gravitational acceleration. And of course, this is a constant. And close to the surface of the Earth is always 9.8 meters per second squared. What I'm looking for is the weight of this block of steel. So by definition, the weight is equal to mass times gravitational acceleration. So here, I simply will substitute the values of the two quantities. So that is 20 kilograms times 9.8 meters per second squared. This is going to give me 196 kilograms meters per second squared. Remember that that unit is known as Newton, and so the weight of those 20 kilograms of steel is 196 newtons. Finally, let's talk about Newton's third law, which is also known as the law of action and reaction. Let's put the statement of the law on the board and then I'll explain it. The third law states that if an object exerts force, which we call action, on a second object, the second object exerts equal force, which we call reaction, on the first object. This situation happens when there is some kind of force interaction between two objects. The simplest example would be placing a book on a flat surface. So here is the book. And so the book pushes on the surface with its weight. So the weight of the book points straight down. And so this force pushes on the surface. Well, so if the book was under the action of only this force, then we would expect the book to be moving down, to be falling towards ground. But the book is not. And furthermore, we don't see any kind of bend or deformation on the surface here. So that means that in that system book surface, there has to be a zero net force acting. Then the members of this system, the book and the surface, do not move. There is no deformations, there is no bending, there is nothing like that. So then that means that there must be a force here in this system that balances the weight of the book. And this force exists and it's directed straight up in opposite direction to the direction in which the weight of the book points. And this force is the normal force. So in terms of Newton's third law, the weight of the book is the action applied on the surface. The normal force is the reaction applied on the book by the surface. And the two forces are equal in magnitude and opposite in direction. For normal force, I'm going to use the symbol N. So this is not a unit, this is not newtons, this is a notation for normal force. And so the normal force is equal to the weight of the book. And the two form an action-reaction pair. Action-reaction pair of forces. Another example for such pair of forces would be the gravitational force between the moon and the earth. So here is the earth, here is the moon. So there is gravitational force between the two planets. The moon pulls on the earth with gravitational force, let's call it F moon. At the same time, the earth pulls on the moon with gravitational force, which we can call F earth. And the two forces are equal to each other. So F moon is equal to F earth. And so as a result, the two planets circle around a common center of mass, or orbit around common center of mass. So the moon goes around the earth, but the earth as well kind of goes around the common center of mass. The common center of mass of the system, earth and moon, is inside the earth, but it's not at the center of the earth. It's shifted by a few kilometers. And so the two planets circle around that common center. And this effect, circling, is due to the fact that the gravitational force between the two planets is attractive. So they attract each other, and as a result, they circle around this common center of mass. But this is an example of a pair of action and reaction forces. So one could ask, how do we know that the moon is actually pulling on the earth? Well, if you observe the ocean, you know that there is periods of the day when we have tides, and then when we have retraction of water. So that movement of water is due to the gravitational force on Earth due to the moon. Another example of action-reaction pair of forces is force of friction when a person is walking, or the force of friction between the tire of a moving car and the road. Here is the road, and this is a tire that rotates in clockwise direction, which means that this tire is moving in that direction, to the right. But why would it move to the right? Well, if you look at the contact between the road and the tire, the motion here is the tire is going this way with respect to the road. So then that will generate a force of friction that will be directed this way to the right. And so that is essentially what causes the tire to actually move in forward direction. At the same time, there is another force that is applied on the road, which obviously is very hard to observe since the road is part of the entire Earth. But technically, there is a force that's opposite that causes the Earth to go in opposite direction. Again, this is a minuscule force which is hard to measure, and for all practical purposes, we don't really need to consider when we are explaining motion. But this is an example of action and reaction pair of forces. And so with this, I will conclude the lecture on explaining motion.